this, but not today. So we were in the middle of discussing the wave equation. And along the way, we were formalizing the ideas we had on this DuHamel's principle, which is a very general technique where for linear problems, and we're only looking at linear constant coefficient problems. Okay, so that makes it a little bit cleaner in the presentation, but it's not the general case. It's a very general technique to use the solution of the initial value problem to describe solutions of the problem with no initial conditions, but interior forcing. This is all about time-dependent problems. Although, when we talk about, time and, initial value problems, you can have a time-like behavior in spatial problems as well. So this would apply in those cases also. For the wave equation, though, it's pretty clear, right? We got time, we got space, and the t is the time, the x is the space. Let's go back to where we left off. Okay, so let me share, and let's make some room so we can write some stuff out. So of course we're looking at the wave equation. Right, we have u t is u x x, and we were looking at the Cauchy problem. So that's the problem for all space and initial conditions given. It's a second order problem, so I have to give the initial values and the time derivative initially as well. Just like second order problems from your ODE days. So we were looking at that, and of course we found two problems. Right, one was where we had U0, but U1 was identically 0. And the other one where U0 was identically 0, but we had U1, right? This is the typical thing we've done before, where for these nonlinear, or for these linear problems, we can divide up the data into different pieces, and we can solve them all separately, putting homogeneous values for the ones that we're not interested in at the time. Using using the D'Alembert form of the solutions to the wave equation, we derived solutions for those two. Let me just talk about this one, because that's going to be relevant for what we have coming up. We have the solution to this one. We get u of x and t is 1/2 the integral from x minus t to x plus t. U1, and now I need a dummy variable, and I didn't want to use s, so I didn't know what to put here. So in the notes I've got theta. Okay, if you don't like theta, you can put something else there. We're going to have s as a dummy variable when we're integrating in time later on, so that's why I didn't want to use it here. Okay, so let's just draw a picture. I don't think we did this last time. I'm solving this problem where I have no initial conditions values, but I've got some time derivative given initially, right? That's this problem, right? And I'm looking for what the solution is here at this position. There's no interior forcing. There's no U0, so the solution is all being driven by this U1. And if I draw these lines back with slopes +1 and -1, back to the initial line, then you see that the solution is the integral of U1 on that line segment with a half in it. So it's the integral of these values along here. Okay, well, in what comes up, right, I want to write the process of taking the function U1 and giving the function U of X at a later time t. I want to write that in a very formal way. And so I did that. I motivated you last lecture, for those that were here, as saying, well, it's some process, it's a linear process, so I can make it look like it's kind of like a matrix multiplication, even though these are, you know, infinite number of values, right? Some process by which I take the function U1 and I get the function U at time t, okay? So that's U of X at a particular time t, some function of X, and I get it by doing this process. So now I'm going to go back to the more abstract setting. We looked at the DuHamel's principle for first order equations in time in the abstract setting, and now we're going to do it for the time for the second order equations. I see there's a question coming up. Oh, whoop. I've got to get my, hang on here. Okay, yeah, I got my Slack window up. Okay, so there's a question which is, are we assuming the x-axis does not cross the t-axis at t equals 0? Well, okay, so in this formula, right, as t goes to 0, right, I should get u equals 0, right, because I've given 0 boundary conditions. So this is completely consistent with that, right? Once I'm down here, I'm only integrating on a little tiny piece, right? I got a little tiny triangle, and the bottom is a tiny piece. And as I go to t equals 0, I'm integrating over no distance, so that's 0. But in fact, this problem says that the value of the solution should be 0 at time 0. So this is good. Is that answering your question?
Kind of. I'm a little bit stuck on how the x minus t value can be less than, I guess, what would otherwise be, but I'll figure it out.
Okay, if you come up with a follow-up question, just put it in the chat and we'll go back to it. Okay, so here we are in this, coming up to this abstract setting where I'm going to talk about how you solve the force problem in general. Because what I'm interested in is the forced wave equation. Okay. But in this abstract thing, right, I'm thinking that this f, this is the whole function of x, time t, and u is the whole function of x at time t in this formal way we're looking at it. Just like the same kind of idea as here. And if we're going to talk about DuHamel's principle, which is you can solve the problem with forcing using just the solution with initial conditions. Of course, you have to wonder for these second order problems, like which one of these do you pick, or is it some combination? And it turns out this one is the winner, which is why I reminded you of it here. So I'm going to say formally, right? Because I'm going to be doing some switching of operations and integrals, which, you know, I'm just saying if that all works out, that this is good, will work out for our case. That if this is just like DuHamel's principle for first order equations, if I integrate from 0 to t, the effect of the forcing function, like it was initial conditions for the time derivative, right? And I integrate those from 0 to t, right? Then this solves this problem. Is there an intuitive explanation as to why phi1 is the winner? I'm sure there is. I haven't got one in my head. For me, this is just the algebra, how it works out. It's an excellent question. I don't even have an intuitive answer for the easier question in the first order problems, right? That the response to interior forcing is the same as an integral of the response to initial conditions. Hey, there's a whole pile of physics students in the audience. If you guys have got a good answer, yeah, let me know. It doesn't have to be, yeah, today. Okay, so let's look at the properties of this thing. Well, I know that this is the one that solves the problem with no initial conditions, right? And derivative conditions equal to whatever this thing multiplies by. So I'll say this is the identity operator. So what's the other thing I know is that phi1 times u1 solves this problem with f identically equal to 0, and that it has to do that for any u1. Any initial conditions you give, this is supposed to solve that problem. And I'm getting the right initial conditions, right, with these conditions. But that it solves this problem is phi1 double prime times u1 should be L times phi1 times u1. And this has got to be true for any time and any function that you operate on, okay? That's what it means to be, that's what it means for this thing to be a solution of this problem with f is equal to 0 and the right initial conditions. So now I'm going to take this u, which I say solves the forcing problem, right? And I'm going to see if, and I want to solve the forcing problem with no initial conditions and no initial time derivative. Now I'm going to see if this thing really does solve it. Okay, so again, I'd love to have more blackboards, right? But write this down on a little sticky somewhere. This is the thing I say it's going to solve my forcing problem. Right, so I've got to show that it has 0 initial conditions, that the time derivative initially is 0, and that if I take 2 time derivatives, it's going to be L times this thing plus F. Okay, so let's go through. If I just look at it, I can see right away that U at time 0 is 0. Because I'm integrating from 0 to 0. Okay, that's good. Now let's take the time derivative of that thing. That's the star. T appears in 2 places. It appears here and here, right? So I've got to use the derivative of an integral, fundamental theorem of calculus. That'll give me 1 term. And then I'll integrate a partial derivative with respect to time. So the first term is phi 1 at 0 times f t, right? But this is 0, right? So this whole thing gets canceled out. And then I'm going to have the integral from 0 to t, phi 1 prime t minus s f of s ds. Okay, and now I can look at ut at time 0, and I see that that's 0, because this term is gone, and this is an integral from 0 to 0. So that's another property I wanted in the initial conditions, so I got that. Okay, well, now I'm going to take the time derivative again. It's the same structure, right? I've got a t here and a t here, so I'll have 2 terms that come. One is from the top boundary. So that's phi 1 prime at t minus t, right? So at 0 times f of t. And remember, phi 1 prime at 0 is the identity. So here is where my f of t is going to come from. Right, and now here I've got the integral from 0 to t. Now I've got phi 1 double prime. But now I'm going to look back here and go, if I take phi 1 double prime of anything, I get L1 times phi times the thing. And I'm going to take the L out of the integral. Oh, sorry, I got the L already. Let's not do 2 L's. Hang on here. What have I got? Phi 1 t minus s f of s ds. And this thing is L times u. So I get UTT is L of u plus f of t. Okay, so this is a formal derivation of DuHamel's principle for second order equations in time. If you can use your imagination or your power of optimistic extrapolation, if you have a problem that's third order in time, then the initial conditions, which are the second derivatives that you have to give initially, that's going to be the operator you want to integrate against the right-hand side data to get the solution, and that's how it works. And you can use this formal derivation to show that. Okay, well, so that's pretty formal stuff. Let's turn this idea loose on the forced wave equation and see what comes out. Because you might be a little suspicious of all of this and everything, what I'll do is I'll use DuHamel's principle to formally get the formula for the solution, and then we'll check that it actually works, right? That you can actually put it in the wave equation, take derivatives, and it matches up the way we want. So let's look at the forced wave equation now. Okay, I see there's a question coming up. The question is, I'm still a bit confused about what it means to be time-like for a variable. It seems like in this wave equation, the only difference between x and t is that t has the initial conditions and forcing function. Well, the forcing function is a function of x and t. So, okay, let's take that out of the mix. The reason why we can call t a time-like variable in this case, it's because that's the kind of initial conditions that were given, right? We gave initial conditions at x equals 0 for u and its time derivative. And so that's then like this flat line that now we're moving away from that flat line. That's what's making it a time-like direction. Now, if we happen to call the variables t and x, but we gave initial conditions on a line, that was x equals 0, then x would be the time-like variable. And someone would say, your notation sucks, right? Because you want to look at it and go t is time and not not be confused by that. But yes, right? Yeah. In this case, you can look at that. It's a good observation, right? There's nothing in that equation that makes you think x is different than t. In fact, it's the initial conditions that are pushing which one is the time-like variable. Okay, so we're going to do this, right? We worked out before that if we're solving initial conditions with a time derivative but no function value, right? This is what comes out. And so now, by the formal process above, we should get a solution to the forced wave equation as an integral of phi1 of t minus s times f. And remember, this is like a process that takes a whole function of x and gives another whole function of x. Right? And what's the whole function that comes out? It's the integral from x minus, okay, well, I'm not going back all the way, right, here to time 0. I'm just going to back t minus x, t minus s. And I'm integrating then f of theta of s d, let me get the order right, theta ds. Right? So this is the story that should come out. Now, it seemed like there was a lot of formal stuff. And so, like I say, I'm actually going to take time derivatives and x derivatives of this thing, right, and show that it really does satisfy the equation. Just in case you were, wondering about the whole validity of that. But before I do that, let me show you a picture of what this looks like. Right. So here I am at a point xt. Right, and I know that the solution to this problem with forcing, right, is an integral in time back to time 0 of f, but it's also an integral in space of f. And if you look at the integral, it's just the straight integral of f on this triangle. right? And even if we added in initial conditions, right, then if we have U0 initial conditions, right, then they influence the solution just at the average of these 2 points, right? And if you include initial conditions for UT, then you've got the integral of those initial conditions on this line. And you notice that doesn't change the values or the places that influence the solution here. And this thing in the lingo of wave equations, hyperbolic equations, this thing is called the domain of dependence. And you can include the initial conditions on this line, right? These points and this line segment are also in the domain of dependence if you include the initial conditions. So let's think about this. This is quite different from the heat equation, right? Where, right, the domain of dependence was, well, right, at xt, every point, right, every point beforehand, right, influences the value here. And it's also true for Laplace's equation, has a global dependence. We've only seen that for the sort of 1D boundary value problems, which are like the 1D version of Poisson and Laplace equation, but there's a global dependence in those cases. And here, right, F can be anything out here, right? Anything at all, right? The world could be exploding out here, right? And it won't influence the value at this point. The only things that tell you what's happening here are in this triangle. So that's kind of interesting. That's very typical of hyperbolic problems, is this very sharply defined domain of dependence. Okay, so I said we would check this explicitly. And in a way, this is basically just doing the formal work that we did to derive DuHamel's principle for second order problems in reverse for this concrete example. But I think it's a useful exercise to do anyway. Anyway, so when I say check this, I should get U of 0 is 0. I should get UT at time 0 should be 0. And I should get UTT is equal to UXX plus F of X and T at all X and T. Right? So let's check and see whether those things go on. Well, I can just look at this and go, at time 0, I'm integrating from 0 to 0, so that one's good. Okay, I got that. Now I'm going to take the time derivative of this. Oh, that's going to be interesting, right? So I'm going to take the time derivative of this, which means I have 2 pieces, right? I've got a t here and I've got a t here, right? So I'm going to have to take the derivative up here. That'll be the fundamental theorem of calculus. I'll get the argument at time s is equal to t, right? And then I'll also get something where I have to take the derivative with respect to t of this stuff, right? Well, there's no actual t inside, so the only contributions there I'll get from the upper and lower limits. Okay, so let's see how that goes. So I'm going to take ut. And I think I forgot a half, right? There's a half here and a half here. Sorry. All right, that's in the definition of the solution with initial conditions, initial time derivatives given. There's the half. Forgot the half. Okay, so now I'm going to take the time derivative of this. I'm going to get the 2 pieces, one of which the second piece will have two contributions, right? Because I've got t in the upper and lower limit. So first of all, I'm going to get 1/2, and then I'm going to get this thing evaluated at s is equal to t. So I'm going to get the integral from x to x, f of theta and s d theta. Okay, well, and this is going to be 0. Okay, now I'm going to have the integral from 0 to t, 1/2, the integral from 0 to t. And what am I going to get? Well, I'm going to get the contributions from the upper and lower limit, right? And I get to put those contributions in, because I'm integrating with theta, I have to put in those values into the function f. So I'm going to have f at okay, I'm missing an argument in the next one. So this is the integral with theta. So I'm going to have f at x plus t minus s and s. Okay, so that's missing from the notes, right? And then I'm going to I've got a lower limit. I'm subtracting, but remember I'm taking the derivative with respect to t, so that's going to change the sign as well. I'm going to have plus f at x minus t plus s and s, and all of that I'm still going to integrate in time. Oh. Okay, so I'm going to look at that expression, and I'm going to go the time derivative at time 0. That's 0. Okay, so that's the other thing I have that I liked. And now I have to take the second derivative in time and see if I get that. Oh dear. Okay, so UTT. What's that going to be? Oh. UTT is, well, I got 2 pieces. Okay. I got 2 pieces, right? The same as before. So one of them is going to be 1/2 1/2 times, well, if I take the, oh, no, I think my 1/2 is going to cancel here. Let me just be a little bit careful. When I take the derivative with respect to t, I get this thing evaluated when s is equal to t, right? So now I'm going to have 1/2 f of x t plus f of xt. So this is going to be f of x and t, right? So that's kind of hopeful, right? Because we wanted that to show up in this expression. And then I'm going to have 1/2 the integral from 0 to t. Now I have to take the derivative of this stuff, right? And that's just f prime at x plus t minus s. And then I'm going to have minus f prime at x minus t plus s. Oh, and this is also evaluated at s ds. Right? Easy peasy. Okay. I spent a little while getting the algebra right in the notes. And you notice I forgot the half at various places. Okay, so if I'm going to try and show that this is true, now I have to take that expression and take the x derivatives, right? Well, okay, let's take one derivative. Oh, yes. I should say this is a function f of x and t, so I'm being a little bit sloppy. these things here, these are the derivatives of f with respect to the first argument. So yes, the derivatives of f with respect to x. Excellent question. Okay, so now let's take derivatives with respect to x and hope that we get this expression, right? Because then UTT would be UXX plus f of x and t, the way we want it to be. Okay, so if I take one derivative with respect to x, okay, I'm not doing anything right here. I'm just taking the derivative with respect to x. So I'll get two pieces. Right, I'm going to get 1/2 the integral from 0 to t. Now it's going to be f of x plus t minus s. But now it's going to be minus, right? Because I'm doing it with the lower derivative, but the sign changed here because I was taking the derivative with t, but here it's not. F, and s, which I forgot in the notes. F of x minus t plus s, and then I'm still integrating in time. And when I take uxx, now I take the partial derivative. Okay, and now I can look at these two things together. Right, and if I look at those two things together, I can see that UTT is UXX plus F. Now, this is kind of interesting. It's one of the great things about mathematics is, you know, this abstract thinking of this DuHamel's process, right? Well, this is something that's true for any kind of linear operator L and a second order problem, right? That's led us to a concrete formula for this particular problem. Oh, there's a question. How did we show that UT was 0? Oh, I just looked at this one. And go when this term is 0. And when I look at the integral here, right, I'm integrating from 0 to 0. That gives me that the time derivative at time 0 is 0. Is that clear?
Nice.
Yeah, yeah. So anyway, back to the kind of big picture point. It was the abstract thinking of this DuHamel's principal argument that gave us this concrete problem for, or this concrete solution to a problem where actually people are really interested in, right? Waves and how they behave. This is a very useful result. Extremely concrete, right? This is a, how do you figure out the value of the wave equation at this point? It's given as an integral of the forcing function over this triangle. Now, could you have derived that formula with some sort of physicsy argument without knowing DuHamel's principle? Maybe, but this was much more straightforward. Okay, much more straightforward with a detour into abstraction. Okay, I've got one last DuHamel thing for you. Okay, I promise, it's the last. Okay. So let me, I won't put down I promise here, but I'll put one last thing here. The last DuHamel thing is, in fact, we shouldn't have done any work to figure out phi1. Oh, a question's coming up. Oh, there's a question which is, I'm having a bit of trouble seeing the difference between DuHamel's principle and a Green's function. Is there a nice way of saying how they are different? This is a Green's function for the solution to the forced wave equation. Right, and phi1, right, this is a Green's function for the solution of the initial value problem with time derivative given function value 0. So those are Green's functions, right? DuHamel's principle is a relationship between those Green's functions, right? It's saying these things are not independent. I get one, that forcing one, by integrating this other one, right? So their Green's functions are Green's functions, right? Both of these are Green's functions, if you want to call them that. And DuHamel's principle is the relationship between them. Is that clear? Okay. So one last DuHamel thing. I don't know if DuHamel, if this counts as putting his name on it. And that is, you can get phi1 from phi0. Okay. So in fact, the only thing we had to work out was phi0, which is the solution to the pure initial value problem with initial values given and time derivative value 0. And we could have got the other one. So it is possible to get phi1 from phi0. Okay, so let's remember what these things are. Both of these solve UTT. Let me do it in the abstract setting, right? Phi1 has U at time 0 equals 0 and UT at time 0 given, right? And the other one has U at 0 given and UT at time 0 equal 0. Okay, and let's recall that this guy has phi at 0 is the identity, and a phi1 or phi0 prime at 0 is 0, right? That's to match these initial conditions. And phi0 double prime times anything is L phi0 times anything. And we could write this shorthand. It's just that the operators phi naught double prime and L times phi naught are the same. If you want to put in the U everywhere, you can do that, right? So my claim is, once you've got this one, you can get the phi1, whose properties we wrote out just a few pages ago, okay? And it's phi1, here's the formula. It's the integral from 0 to t of that operator. So now I'm being really formal, right? because I can look at phi1 at time 0. That's 0. Right? Okay, well, that's what we wanted. I can take its time derivative. That's got two pieces. I've got phi 0 at t minus t. That's 0. That's the identity. Plus the integral from 0 to t phi naught prime t minus s ds. So phi 1 prime at 0 is the identity. We wanted that. We wanted that. And now we want phi 1 double prime is L times phi 1. Okay, so now I'm going to have phi 1 double prime. That's going to be equal to phi naught double prime. But phi naught double prime is just L times phi naught. And that's just L times this thing, which we call phi 1. So it's just one of those fascinating things about linear systems that everything about how the system, this is, I guess, sort of the big takeaway thing. Everything about the linear system, time dependent. Everything about its behavior is determined by how it behaves to initial conditions, values, no time derivatives, right? How it behaves to initial conditions without forcing, right? And then you can understand how it behaves with other initial conditions and with forcing based entirely on that. And just in case you need the concrete example, right? We've worked out phi 1 and phi 0 for the wave equation. So let's check that phi 1 of t is really phi naught of t minus s ds for the wave equation. Right? Well, I can check it by seeing that if I look at how it operates on something. So this is got to act on a function, right? On this is going to be the v1, the initial. This is going to be the initial conditions. I'm going to look at it at a function at a point x. All I do remember is I average the values behind and ahead by time t minus s. Bracket. And so if I integrate that, I get 1/2 the integral from 0 to t. I'm going to get v x minus t minus s plus v x plus t minus s. And now you have to do a little bit of thinking. I'm integrating v with some arguments. And this one has an argument that goes from x minus t to x. And this one has an argument that goes from x plus t to x. And so if you think about it, that's exactly the same thing as integrating from x minus t to x plus t of v of s ds. Right, which was exactly our formula for phi 1. So formal, yeah, but all very interesting, and tells you something about the behavior of linear time-dependent systems in a really profound way. We're going to go on, we're going to talk about boundary conditions. Before that, I've got a poll for you. I think I have a poll for you. It's a follow-up poll from last time. Last time it was the list of topics we've had so far this year and which ones you liked most or hated least. And now it's which ones would you like additional notes for? I put updated with more explanation and examples. Oh, it's a close race. There's 3 people left who will decide the fate of Math 400. One person left. One person is sleeping. Well, okay. I could have had another cup of coffee, and I'd also. Oh no, they woke up. Okay, so I'm happy to write up some more notes on asymptotics. I have to say, in this particular course, asymptotics is just a sort of sideshow. You know, it's a useful technique that augments the kind of work that we have been doing. There is a whole course on asymptotics. It's math. It's a graduate class, cross-listed as an undergraduate class.
Isn't it 450/550?
Math, I was going to say, could be 450.
Yeah, it is 450.
Yeah. Has anyone taken it? Anyone out there? Okay, so if you really want asymptotics, that's full-on asymptotics. Okay, so that's you know that's the whole meal deal. I'm giving you a flavor in this class, and I am happy to update the notes and put because we've talked about it in a few different contexts in a more coherent way. I won't promise it for next week, but sometime in the next 2 weeks. How about that? Okay. Thanks for the input. So of course, we've still got some stuff to talk about the wave equation. And it's about boundary conditions, right? So we've looked at the wave equation in this Cauchy problem format where it's like the infinite string, the infinite stretch string. Well, yeah, what happens when the waves hit the where the string is tied up to the wall, right? So let's talk about boundary conditions. Let me do a concrete thing, and then I'll draw you a little picture afterwards. Oh, there's a question which the student has said it's a stupid question. I don't think any questions are stupid, particularly. What is asymptotic analysis used for? Like a more formal definition of how the epsilon provides info for us. So let's think about the kind of solutions that we have come up with, right? We've come up with solutions for pretty, okay, because we're writing stuff out with, you know, pen and pencil, right? We're coming up with solutions for things that are pretty simple, right? You have constant coefficient, linear problems, right? What asymptotic analysis is useful for is getting insight into when you don't have constant coefficient problems anymore, right? But you're close to a constant coefficient problem. So after Math400, constant coefficient problems, you're going to really understand, like, deeply, right, how they behave. Then you're in this sort of, let's say, engineering question, what science question, right? Like real science, right? Not abstract. You know, what if we change the properties of our device a little bit, right? Is that going to make, you know, more photons or less photons, or, you know, whatever you're trying to do. So it's really this sort of, if you like, it's the extension of first year calculus, where you were doing, you know, linear approximation of functions, right? So you have a complicated function, it's hard to sort of say what's going on, right? But if you have a straight line, right, it's easy to understand, you know what's going on. Increase a little bit and it'll go up a little bit with the multiple. That's the derivative. And so asymptotic analysis is really, if you have a real understanding of a basic problem and you're interested in changes to that problem, you know, if you make small changes, what kind of small changes will come in the outcome? And, you know, it does two things, right? Once you get into problems that you can't find analytics solutions for, you can do numerical computation. Well, I'm a scientific computing guy, so I think, yeah, compute. But, you know, computing a bunch of cases does not give you the same kind of insight into, you know, the quantity you're interested in changes like 4 times epsilon if you have this shape of change in your system. So it's okay. So now I've talked quite a bit. I don't know if I've answered your question. I'm not an asymptotic expert. I've found that asymptotics, it's been really useful in understanding things in my applied research. So, okay, I'll try and give some more words of the big picture in these notes that I've been encouraged to write up. Okay, so we had the Cauchy problem, no boundary conditions. Let's put in one boundary condition. Okay, so it's like okay, let's start small, right? So now I'm going to be interested in the wave equation, not for all x, but for x bigger than 0. I want to solve the wave equation, right? I want to give the problem with initial conditions and no time derivative initial conditions, right? No forcing. So this is this is problem, 0, but now right, you can get all the other solutions out of this one. Okay, and so one of the things that we know, right, is that some information propagates to the right and some information propagates to the left. I can tell you, but I think I can also motivate you to say, we need one boundary condition here, right? It's second order derivatives in X, but we really only need one piece of information traveling to the right to come out of this boundary, and that's going to be u equals 0. So if this was the infinite, semi-infinite stretched string, then this boundary condition would be, remember, u is like the vertical displacement in the stretched string that has got wave motion back and forth. So setting u equals 0 just means you've tied the string and it can't move up and down at that point, right? Okay, so you've tied the string. So this is u equals 0. This is for all t. Now what's interesting is D'Alembert's solution still applies, right? It's the wave equation. Okay, you put in a boundary condition, but it's still true that in 1D wave equation, you can write the solution as some function of x minus t. Okay, and now I'm going to remember not to use g but b for forward and backward. Right, for some f and b. I'm going to say g at some point and I'll get confused, but let me try and stick with b. So this is still true, right? And we can do the same algebra we did, right? And know that f of s is 1/2 of u0 of s. And I was about to write g. B of s is 1/2 of u0 of s. This is matching the conditions. This is for s bigger than 0, because I've got initial conditions for arguments that are positive. So positive arguments are enough for this b function, right? I'm sitting out here, x is positive, t is positive. I'm only putting positive arguments into here, right? And I know what all of the positive arguments of b are. Okay, I'm done, right? Okay, but we need negative arguments for f. And if you think about it, right, if I've got x minus t, where does that switch between being positive and negative? That's x is equal to t. That's a oh, that's not t. Right. Everything is fine out here, right? We know what's going on, but in here we don't, right? But if you think about it, right? This is the f where we need the arguments that we don't have over here, right? This is where the forward wave is coming from the boundary, not the initial conditions, right? So we're going to be able to fill in the question mark with the boundary conditions. So let's look at the boundary conditions. That's u at x equals 0 for all time. Well, I've got f of x minus t, so this is f at minus t. Oh, this is good, right? I need the negative arguments of f, and this is where they're going to come from. so that tells me, now I'm gonna think about this a little bit different, right? I want to talk about the arguments of f, right, which can be negative. So I can look at f of s, that's for s less than or equal to 0. These are the ones I need. And just thinking about this a different way, this is just minus b of minus s. And if s is less than 0, then minus s is positive. I know all the positive arguments of b, right? So this is fine, right? And this is minus 1/2 u0 of minus s. So the solution is u of x and t. It's, okay, well, when x is bigger than t, everything's determined by the initial conditions. So I get the usual 1/2 u0 x minus t plus 1/2 u0 x plus t. Right, and when x is less than t, right, I've still got the 1/2 u0 x plus t, right? But now over here, I've got a minus 1/2 u0. Now I have to be a little bit careful. Now it's minus x minus t. Now I have to think about this for a minute. X is equal to t. It'll be continuous. So pick whichever one you want. Right. Hopefully that is continuous. Okay, now I have to think about this for a minute. F of s. Yeah, okay. So there's an interpretation, right? Okay, and that is if I had a bump that was here, right? This is the x and t, and I'm overlaying this plot with u0 of x. So you know the game that happens, right? Is these initial conditions break up into two pieces. One goes forward, one goes backwards. Okay. Right? And when you are out here, right? When you're up here, right? So this is this x later time. I guess I should, yeah, I've got later time out here. Okay, let me draw this again. Ooh, rainbow. So now I'm looking way out here, right? This guy is still going out, right? This one, right? But this thing here, right, is, oh, no. Now I see where I've gone. I've got my head mixed up. This guy, on this picture, this guy has disappeared off the scene once I've gotten really late, right? But it's replaced by something that looks like this inverted thing moving forward, right? So that's what this term is. this is this thing here hitting the wall and returning, but inverted. So this is an inverted reflected wave. That's this thing here. So you have wave-like behavior. Boundaries introduce reflection, and there's some interesting things you can talk about with reflection and transmission coefficients, which will show up on the next assignment. We're at 10:43, so let me just tell you, so next time, we didn't get out of the lecture 13 notes. So now we've got the lecture 14 notes, which I'll do in lecture 15. Again, it's like when I cook, I make sure there's more than enough. So same thing with lectures. So next time, we'll look at bounded domains with boundary conditions. And there, we can also think of the behavior as, transmitted and reflected waves back and forth. But funnily enough, it's actually more useful to think of series solutions. So we'll have a little bit of a reprise of our expertise in series solutions will come back next time. Okay, so that's it for today's lecture. I'm going to stop recording, but as usual, I'll stick around if anyone wants to ask questions.